Hey everyone, I am Miss Hu, your physics teacher. In this video, we are going to go through nuclear energy calculations. What we'll be covering in this video lesson are Einstein's equation of mass energy conservation, as well as how to use the equation to solve problems. This is a topic in the SPM physics syllabus. There's of course a lot more to know about this topic and many variations of questions to solve. There's of course a lot more to know about the calculations. So if you'd like to find out more, please do your own research, do your own practice, or watch my other videos where I will also cover some questions and how to solve them. In the meantime, let's get started. So first of all, we need to recognize Einstein's equation of mass energy conservation. The formula is very simple, and in fact, this is a formula that I'm sure all of you have seen throughout your entire lifetime up to now. Even though you have no idea what it meant, you'll be like, yeah, this is Einstein's equation. What's it for? I don't know. Well, now you'll learn. So the formula is the famous E equals mc squared. What are all these symbols representing? So E in this case is of course energy, which in this case is the energy produced from a nuclear reaction. So this is energy, and energy is of course written in units of joules, which I'll write here, joule, or short form is J. M in this case, well, M is normally mass, right? In this case, you have to know specifically that M represents mass defect. Mass defect is a very fancy way of basically saying loss in mass. This must of course be written in SI unit, and the SI unit of mass is kilogram. Short form is of course kg. Now, if you're wondering what is mass defect, what you should be aware of is that every time a nuclear reaction happens, it could be a radioactive decay process, for example, alpha decay, beta decay, gamma decay, or it could be a nuclear fission reaction or a nuclear fusion reaction. Whatever the case is, before and after, the mass does not stay the same. Because if you recall, for radioactive decay, what happens is that the nucleus will throw out a particle for alpha and beta, leaving behind a different nucleus. So basically, a large nucleus splits into one slightly smaller nucleus and one very, very small particle. Even for nuclear fission, one large nucleus splits into two smaller. Nuclear fusion, two smaller combining into one larger nucleus. So there's always something happening with the nucleus, splitting and combining and all that. So before and after the reaction, the mass does not stay the same. The mass actually decreases. That loss in mass was converted into energy. So that's why M is not mass. M represents the mass defect, which is also the loss in mass. C, in this case, is a constant value, which is the speed of light. This value is a fixed value, and the value is 3 times 10 to the power of 8 meters per second. Let me just move this a little bit so that you can see it more clearly. Meters per second. Let's put this a different color just because. So what has the speed of light got to do with the energy conversion? It's a little bit technical. It's something to do with the way that when a mass travels and it gets close enough to the speed of light, the speed of light will somehow affect the mass to be converted to energy. We don't have to get to that level of technicality. You just need to know how to use the formula. So E represents the energy that's produced. M is the mass defect. And C is a constant value of the speed of light, which is 3 times 10 to the power of 8. And to use this formula, we have to square the value of C. Now, let's take a look at a few questions and how to solve them using this formula. So let's take a look at this question. So question 1. The sun uses its mass at a rate of 2 times 10 to the power of 9 kilograms per second to generate energy from fusion. If the speed of light is 3 times 10 to the power of 8 meters per second, calculate the energy generated by the sun per second. So to solve this question, we just need to use the formula of E equals mc squared. So I'm going to write that out here. I'm going to use a different color just to make it pop. So E equals to mc squared. So in this case, we are calculating the energy produced. Now, although they've given us the mass at kg per second, it just means every second this much mass is being used. And they are asking how much energy is generated per second. So we're just going to use the mass every second. In this case, 2 times 10 to the power of 9. For the value of C, it's the constant value of the speed of light. So it's 3 times 10 to the power of 8. And remember to square the value of C. So a lot of students, they don't get the correct answer because they forgot to square it. And the answer we'll get is 1.8 times 10 to the power of 26 joules per second. So now let's take a look at a question that uses a different unit for the mass. So here, question 2, in a nuclear reaction, 0.05 AMU of a radioactive sample is converted to energy. If 1 AMU is 1.66 times 10 to the power negative 27 kilograms and the speed of light is 3 times 10 to the power of 8 meters per second, calculate the nuclear energy produced from the nuclear process. So if you're wondering, what is this AMU? Okay, let me just write that out here. AMU stands for atomic mass unit. If you learn chemistry, it is very similar to the concept of relative atomic mass, but similar but not exactly the same. So what exactly is this atomic mass unit? One atomic mass unit is equivalent to the value of 1/12 of the mass of a carbon-12 atom. So remember that when it comes to atoms, sometimes when we want to compare the mass, we don't want to take the value in actual grammage or kilograms when we are talking about comparing the mass between different atoms. So for example, you learned in chemistry relative atomic mass. So the relative atomic mass of an atom, say helium, is 4. That means it's 4 times heavier than 1/12 of a carbon-12 atom. A simpler way would be to compare it to hydrogen, of course, because a hydrogen atom has mass of 1 unit. So helium is 4 times heavier than a hydrogen atom. But why we don't say hydrogen in this case is because historically, when we want to come up with the definition, we used carbon as the standard instead of hydrogen. So that's why the definition uses carbon instead. So 1/12 of a carbon-12 atom. Carbon-12 has 12 units. So carbon-12 has 12 mass units. That's why 1/12 is actually 1 unit. So instead of using grams and kilograms, we just use the relative mass comparing different atoms. So when we say atomic mass unit, we're going down to the comparison of the mass of the different atoms and particles and at an atomic level. That's why we use atomic mass unit instead of grams and kilograms. So if we have 0.05 AMU, that's 0.05 atomic mass units. That means it's 0.05 of 1 unit of one of those atoms. Now, AMU is a unit that we can use for mass, but whenever we want to use the formula of E equals mc squared and we want to calculate energy in joules, you cannot use mass in some other unit. You have to use mass in kilograms. So that's why they've given us the value of conversion here. 1 AMU is 1.66 times 10 to the power negative 27 kilograms. So what we need to do is we need to convert this 0.05 AMU into kilograms. How do we do that? Very easy. Just take 0.05 times 1.66 times 10 to the power negative 27. And this will give us the value in kilograms. Then this has to be multiplied with the speed of light. C, which is 3 times 10 to the power of 8, and we square that value. So in the end, the value that we will get is 7.47 times 10 to the power of negative 12 joules. And that's how we can solve the question with AMU. Now, sometimes we will get a question that doesn't give us the mass defect outright. They could give us a question like this, where they give us the atomic mass units of each nucleus involved in the reaction. And what we have to do before we can calculate the energy release is to calculate the mass defect first. So how do we do this? We just need to take that difference in mass. So I'm going to go to the next slide to do the calculations. So first of all, you need to calculate the difference between the total mass before and after the reaction. So what I'm going to do is I'm going to write here the mass defect is the total before minus the total after. And what we'll get is 0.004 atomic mass units. Now, it would be a good idea to convert the AMU into kilograms right now. So we're going to take 0.004 times the value of the AMU in kilogram, which is 1.66 times 10 to the power of negative 27. And this gives us 6.64 times 10 to the power of negative 30 kilograms. So to calculate the energy, all we need to do is use the E equals mc squared formula. The m in this case is the mass defect, which we have just calculated. So 6.64 times 10 to the power of negative 30 times the value of c, which is 3 times 10 to the power of 8, and we square that. So this gives us 5.976 times 10 to the power of negative 13 joules. So this is how we solve the energy calculation when given these kind of values. So calculate the mass defect first by taking the total mass before minus the total mass after. If it's in AMU, convert it into kilograms, and then just sub the value into the equation to solve the value in joules. So I hope you found this video educational and helpful. Please click like and subscribe for more lessons, solutions, and exam strategies from your physics teacher, Miss Ho. Happy studying!